Hey there, Mr. Sutton here, bringing you the BC Calculus Chapter 7 Quiz 4 Review Solutions on Convergence Part 2. On this problem, I'm going to use the alternating series test to figure out divergence or convergence. So for alternating series test, we're going to use this whenever we see a -1 to some exponential term, or if you have a cosine of pi n that makes you go back and forth between negative and positive 1 as a multiplier, then you would also use the alternating series test. So this test says that if you have a series that is alternating, like this one is, and its terms are decreasing in absolute value to 0, then the series is going to converge. Now the alternating part is easy to pick out, again, as long as you have -1 to some exponent, or if you have a cosine of pi n, that one's a little bit more hidden, but you can learn to spot it. The decreasing in absolute value to 0, though, you have to at least mentally take the limit of the nth term, at least the absolute value of the nth term. So we see if we do that here that we have a bottom-heavy function that will be going to 0 as n approaches infinity. So we can say on this one then, and this is what you actually have to write out, the terms are alternating and decreasing in absolute value to 0. Therefore, this series converges by the alternating series test. For this problem, we tried the nth term test, and we see that the limit here is going to go to 0 as n approaches infinity. We might also think about trying the p-series test, but this is not quite a p-series. We're close, though. So we're actually going to use something called the direct comparison test. This is a great test to try out whenever you have something that's almost a geometric series or a p-series. So in cases like that, we pick a comparison series, which should be fairly close to the original and also easy to figure out convergence for. In this case, I'm going to pick the comparison series of radical n over n squared, because I can reduce that to a p-series, which will be easy to figure out if it converges or diverges. So this is really n to the 1/2 over n squared. Subtracting those exponents, I have n to the 3/2 in the denominator and just 1 left upstairs. So this is an equivalent comparison series. Now this one's nice to look at because this is a p-series with a p-value of 3/2. Since that's greater than 1, we know that this is going to converge. So now I just have to compare it to this series in a way that shows the original converges. Now, in order to get convergence out of direct comparison, I need to show that my original series is less than a converging series. So I need to compare it. I also need to show that both of these series are actually positive for certain n values. So the order here, so for positivity, as long as I'm plugging in n values that are 1 or greater, both of these series are going to come out to positive numbers. And in terms of what's bigger, this series right here is actually, the only difference between this series and our comparison series is this little +1 down here. If I have a larger denominator, that means the overall fraction is smaller. So we can say that this series is smaller than radical n over n squared. And both series are positive. So to write all of that out in one shot, I'm going to say 0 is less than or equal to radical n over n squared plus 1, which is less than or equal to radical n over n squared. Or you could write 1 over n to the 3/2. It doesn't matter at this point. You do need to specify what n values this is true for, though, because it might not be true for all of them. So we're going to say n greater than or equal to 1 on this one. And once I've made this statement here, and already shown that my comparison series converged, I can say that my original here is going to converge by the direct comparison test. To find convergence on this problem, after unsuccessfully trying to nth term this thing, we're going to use another comparison test. So this is pretty close to 1 over radical n. I think I could compare it to that. So let me try this series. This is a good comparison series because we can very quickly see it's a p-series, p-value of 1/2 down here. Since that's less than or equal to 1, we know this series is going to diverge by the p-series test. So now what kind of comparison should I use? Well, I always look to see if I can use direct comparison because that's usually faster than limit comparison. We see here that I have a fraction that is larger in the numerator than the comparison series. The denominator is smaller. You're taking 1/2 of n and then subtracting 1 inside the square root. Bigger denominator, or bigger numerator, smaller denominator means bigger overall fraction. And that's a good thing because if you have a diverging series for your comparison series, you want to show your original is bigger than that because then your original would diverge. So in order to prove things and write things out, I have to show these are both positive. So I'm going to write that they're both greater than or equal to 0. And I need to show that my diverging series is smaller. So I'm going to write 0 less than or equal to 1 over radical n, less than or equal to 2 over radical 1/2 n minus 1. And I need to specify which n values this is actually true for. If you plug in 1 for n, this is not actually a true statement because then you're taking the square root of a negative number. So I'm going to start at n values of 3 or greater. At 3 or greater, this starts being true. So now that I've made this statement, I can say my original is going to diverge by direct comparison. To figure out convergence or divergence on this problem, as always, we try the nth term test first, and we see that this is bottom heavy, so going to 0, so that doesn't help us. Next, we might think about doing a comparison. Now, if you try comparison on this one, you're going to see that things are going the wrong direction with the inequalities, at least if you try direct comparison. So that's where we try out limit comparison test. This is a great test when you have something that's almost a p-series or a geometric function, and the inequality is not working out for direct comparison. So you've basically already considered direct comparison if you're getting to this point. So to use this test, we need to first pick a comparison series. So I'm going to use n over n cubed because that's pretty close to what I'm starting with here. And I'm actually going to reduce that right away to 1 over n squared, which is a p-series, p-value of 2. That's greater than 1, so this is going to be a converging comparison series. So next, I'm going to need to verify that my comparison series and my original series are both positive, and we see that they are both going to be positive if you plug in, well, really n values of 1 or greater. So I'm going to write this original is greater than 0, and 1 over n squared or n over n cubed is greater than 0, as long as n is greater than or equal to 1. Now that I've done that, I'm going to take the limit of the ratio between my original function and my comparison series here. So I have limit as n approaches infinity of all this stuff divided by 1 over n squared. You could use n over n cubed down here, but I usually like to use the most reduced version so I don't have to do any more algebra than I need to later on. So now we have to simplify this fraction, same change flip. I've got 4n plus 9 times this n squared that's coming upstairs. And then the denominator, I just have 2n cubed minus n times an invisible 1. Now if I actually multiply this all out and ignore the lesser terms because n is growing to infinity, upstairs I have a 4n cubed. Downstairs it's just 2n cubed. That's just going to reduce to 2. Since 2, which notice I wrote L equals all this stuff so I can use it later, since 2 is a number that is finite and positive, since it's between 0 and infinity in other words, that means that since my comparison series converged, my original series is going to converge by the limit comparison test. Figuring out convergence on this one, my nth term test doesn't help me out because this is going to 0, so I try some other things. This is close to the p-series 1 over n, so I'm going to compare it to that series. Now this series is very easy to figure out convergence for. We know this is the harmonic series, which is known to diverge without any further proof. So I'm going to try a comparison test now using the harmonic series. Now if we look at what's going on here, this original, it's larger in the numerator, which is a good thing, but the denominator is also bigger, which would drag the fraction down. So it's kind of ambiguous whether this thing is always greater or always smaller than the harmonic series. In cases like this, we just go straight to limit comparison, which doesn't require us to be greater than or less than. So in order to use limit comparison, again, I need to make sure that I have positive functions. And these are both positive. There's no way these are going to come out negative for any n values that are greater than or equal to 1. So I'll write 3 over 5n plus 7 is greater than 0, and 1 over n is greater than 0 for n greater than or equal to 1. So now I take the limit of the ratios of these. I've got limit as n approaches infinity of 3 over 5n plus 7, all of that over 1 over n, and I'll let whatever this comes out to equal L so I can use it later on. Same change flip. I've got 3 times n in the numerator over 5n plus 7 times this invisible 1 in the denominator. As n approaches infinity, this 7 is just we can just ignore it. So we just have 3n over 5n, which is 3/5. Since that is a number between 0 and infinity, it's finite and it's positive. That means that since our comparison series diverged, the original diverges, behaves the same way by the limit comparison test. On this problem, we're trying to figure out if this expression converges absolutely, conditionally, or diverges. In situations like this, we always test for absolute convergence first, which means that the series would converge if you take the absolute value of the expression. Conditional convergence means it converges only if you leave the alternating in, so if you allow for negative terms. And then diverging is what it is. So first we check out the absolute version value, or absolute value version of this, which is just 1 over n times 4th root of n. Now this can be rewritten as 1 over n to the 5/4. This is really n to the 1 times n to the 1/4, so that's 5/4. That's a p-series with a p-value of 5 over 4. Since that's a number that's bigger than 1, we would say that this converges by the p-series test. And since the absolute value version of this thing is what's converging, we would say this whole series converges absolutely by the p-series test. Now, if something converges absolutely, then you're done. You don't need to test to see if it converges conditionally because it's one or the other. So that means that we can move on to whatever else we have going on in life. On this problem, we want to figure out absolute versus conditional convergence. So it helps if you realize that what you're really dealing with here is -1 to the n over n. Because if you plug in 1 for n here, cosine of 1 pi is -1. Cosine of 2 pi is going to be +1. So this keeps flipping back and forth between negative and +1, just the way cosine works when you take a cosine of multiples of pi. So now, since this is our series and we're testing for absolute versus conditional convergence, we first consider this series without alternating. So we're going to consider the series just 1 over n and see if that converges or not. Now this we very quickly see is the harmonic series, which we know diverges. Since we failed absolute convergence, we still have a shot at conditional convergence. So that's where you look back at the alternating version of the series and see if that converges. And if it still doesn't converge, then we'll say it diverges at that point. But this series here, this original, is actually the alternating harmonic series. In general, we can say that the terms of the original alternate and decrease in absolute value to 0, or we can say it's alternating harmonic, one or the other. So this is going to converge conditionally then by the alternating series test. And by the way, if you worded this as saying that the original was the alternating harmonic series, then you would still say we converge conditionally by alternating series test, because alternating harmonic series is just a special case of this test. For this problem, they're asking for the interval of convergence. So with interval of convergence, if you have a geometric series, then you just set the common ratio, the absolute value of that, less than 1, and write it without an absolute value, and then that is going to be your interval of convergence. If you do not have a geometric series, like in this case here, it's not quite geometric because of this n to the e term downstairs, then you've got to use the ratio test. So we'll use the ratio test on this one. So we've got limit of, as n approaches infinity, of absolute value of n plus 1th term over nth term. So we have e to the n plus 1, x to the n plus 1, n plus 1 to the e. All of that is in the numerator of a big old fraction inside an absolute value with an infinite limit. In the denominator, we have the nth term, which is just going to be all this stuff in the original series. Now we're going to do same change flip, multiply by the reciprocal to reduce this fraction. So in my numerator of my new fraction, I have an e to the n plus 1, x to the n plus 1, and I also have n to the e. Denominator, we've got n plus 1 to the e to the n, x to the n. And I can reduce a few things here. The e and the x terms, those can actually reduce by subtracting the exponents. So we're just going to have e to the first power and x to the first power upstairs. Nothing else I can really reduce. So let me just rewrite what I have. So I have ex n to the e right here. And then in the denominator, all that's left over is n plus 1 to the e. Now, as n approaches infinity, this little plus 1 next to the n is we can just ignore it. So I just have an n to the e downstairs. That's going to cancel the n to the e upstairs, leaving us with just absolute value of e times x. And at this point, once you've got rid of the n's and the limit as well, you set this less than 1. So I can divide both sides by e, so I just have absolute value of x is less than 1 over e. And now for my rough draft of my interval of convergence, I'm going to rewrite this without an absolute value. So I can say negative 1 over e less than x less than 1 over e. But because I used the ratio test, which is ambiguous when this stuff equals exactly 1, I have to actually test these endpoints to see if the endpoints converge. I wrote less than right here, but either of these could be less than or equal to as well. If I had gotten all this using the geometric series test, then these would be less than no matter what. Because I use ratio test, I need to test the endpoints. So if x equals negative 1 over e, we plug that back into the series and see what that does to the overall series. If we have negative 1 over e for x, e to the n times negative 1 over e to the n, well, I can combine those just to get negative 1 to the n over n to the e. And this is a series that alternates, and because my denominator is growing, this is also going to decrease in absolute value to 0. Since I have all that, this is going to converge by the alternating series test. So I'm going to have to rewrite this inequality with an equals under it in just a moment. But let me test out 1 over e. Let me test out that other endpoint first. If I have e to the n times 1 over e to the n, those are just going to cancel out, leaving me with 1 in the numerator. So now this is just a plain old p-series here with a p-value of e, which is kind of weird, but that's a number bigger than 1, so that means this is going to converge by the p-series test. So since I converged at x equals negative 1 over e, that means I have to write negative 1 over e is less than or equal to x. Since I also converged at 1 over e, I have to write again less than or equal to 1 over e. But if I had diverged here, I would have just kept it as less than with no equals. So this is my final interval of convergence.